Okay, I want to do a few more examples here since the short little videos that you had didn't do a whole lot of examples. We were looking at the power rule for integration, so let's go ahead and do some other examples here. Let's try radical. Let's look at the integral of the cube root of x squared with respect to x. Now, when we are doing this integration and using the power rule, what I want is to see the exponents on everything. So I need to rewrite this with an exponent. And the exponent that goes on the x will be x raised to the 2/3 power with respect to x. As a side note here, for those of you who don't know how to do it, what I'm going to tell you here is that you want to keep up with the radical. For example, in this case, if I have the cube root of x, keep up with this number, because when you rewrite this as a fraction, that's the number that goes on the bottom, and anything left on the x is going to go on top. So in this case, this would be x raised to the 1/3. The cubed root of x squared, as we just saw, remember, keep up with the radical. So it's the 3 that goes on the bottom, and then any other exponent you see will go on top. Just one more quick example here, the 5th root of x cubed. Again, keep up with the radical. That's going to wind up on the bottom, and then any other exponent you see is going to wind up on top. So that would be x raised to the 3/5. Once you have this written in its fractional form and written as the exponent, you can go ahead and you apply your product rule, or the power rule, excuse me. This is going to be x raised to the 2/3 plus 1 power divided by 2/3 plus 1 power, all plus c. And that's going to give us x to the 5/3 over 5/3 plus c. Now the one thing that we cannot, or one of the things that we cannot have in our answer in calculus is a complex fraction. And a complex fraction is a case where you have a fraction that has additional fractions on the top and or bottom. When you write this, it has to be written as a single fraction. So what we need to do is we need to take this number on the bottom, and of course we're just going to flip it and multiply. So this will become 3/5 x to the 5/3 all. Okay, I want to go through a little bit about the notation. I'm going to go ahead and do this in yellow so you can see me writing on the screen here. First off, when we write math, remember we talked about the fact that math is a language. The first thing you see here is the integral symbol. The integral symbol tells us that we want to find an antiderivative. The other symbol that's important in this is the dx. It tells us with respect to which variable we are integrating. We must have these two things within our problem. As we go through some of the calculuses down the road, we're going to find that we are able to integrate with respect to many variables within a problem. And so even though it looks like it's very obvious right now, it will not be obvious later on. So the dx or the dy or whatever that is has to be there in your problems. Notice when I go to the next line, I use an equal sign to indicate that I am continuing with the same problem. Here I rewrote the x using an exponent instead of the radical notation. I have not integrated yet, so I did not get rid of my integration symbols. It is not until I actually apply the power rule in the next step that I can get rid of the symbols of integration. Once again, we need to be able to add those fractions, 2/3 plus 1. And when we do, we get this complex fraction here. Again, notice I'm using the equal signs to indicate that the problem's continuing. In this step here, we have what's called a complex fraction. A complex fraction is a fraction that has other fractions on the top and or bottom, and that's never acceptable. As you saw in the video, they actually multiplied both the top and the bottom by the reciprocal of what you see. But for me, I just simply remember that if I flip the bottom one and multiply, it puts it on top. So I just took the 5/3, flipped it, and let it become a 3/5. Now, I want to talk about checking these things because as you saw in the video, we are able to check them. In order to check them, we need to be able to take the derivative. When you take the derivative, again, remember, we're writing in this language. I need to know that you're taking a derivative. And there are two ways that you can do this. The way that he did it in the video, which is my preference, is to write d dx 3/5 x to the 5/3 plus c. This notation right here clearly says that I am taking the derivative of these terms with respect to x. And this would be acceptable. You could go ahead and do this and then actually take the derivatives. The 3/5 is going to carry down, and then I'll differentiate the x part. The 5/3 comes down in front, and I take the x and raise it to the 5/3 minus 1, or the 2/3 power. Of course, the derivative of any constant is 0. Here, those fractions cancel out, and I actually get x to the 2/3 plus 0, or simply x to the 2/3, which means it does indeed check. Again, notice I am letting you know that I'm taking a derivative, and then I am using these equal signs to show that I am progressing from one step to the other. Now, that's one way you can indicate that you're taking a derivative. The other way that you can indicate that you are taking the derivative is to go ahead and call your answer y. Taking my answer from the first step, I've got y is equal to 3/5 x to the 5/3 plus c, and I will note that I'm taking a derivative by using the y prime notation, and then I can go ahead and take the derivative and check it, and I should get the same thing. So this is going to be an either or, but you cannot just start taking a derivative on a page. I expect to see some notation that indicates that you are indeed taking a derivative.